Hello. Please hit like button and subscribe my channel. Also press bell icon for future video notifications. Thanks.
Scientists have taken a major step forward in harnessing machine learning to accelerate the design for better batteries, instead of using it just to speed up scientific analysis by looking for patterns in data, as researchers generally do. They combined it with knowledge gained from experiments. It was the first time this approach, known as scientific machine learning, has been applied to battery cycling, said Will Chua, an associate professor at Stanford. He said the results overturn long-held assumptions about how lithium-ion batteries charge and discharge and give researchers a new set of rules for engineering longer-lasting batteries. The research, reported today in Nature Materials, is the latest result from a collaboration between Stanford, SLAC, the Massachusetts Institute of Technology and Toyota Research Institute (TRI). The goal is to bring together foundational research and industry know-how to develop a long-lived electric vehicle battery that can be charged in 10 minutes. Battery technology is important for any type of electric powertrain, said Patrick Herring, senior research scientist for Toyota Research Institute. By understanding the fundamental reactions that occur within the battery, we can extend its life, enable faster charging and ultimately design better battery materials. We look forward to building on this work through future experiments to achieve lower cost, better performing batteries. A trio of advances. The new study builds on two previous advances where the group used more conventional forms of machine learning to dramatically accelerate both battery testing. While these studies allowed researchers to make much faster progress, reducing the time needed to determine battery lifetimes by 98%, for instance, they didn't reveal the underlying physics or chemistry that made some batteries last longer than others, as the latest study did. Combining all three approaches could potentially slash the time needed to bring a new battery technology from the lab bench to the consumer by as much as 2/3. In this case, we are teaching the machine how to learn the physics of a new type of failure mechanism that could help us design better and safer fast-charging batteries, Chua said. Fast charging is incredibly stressful and damaging to batteries, and solving this problem is key to expanding the nation's fleet of electric vehicles as part of the overall strategy for fighting climate change. The new combined approach can also be applied to developing the grid-scale battery SYS. Zooming in for close-ups, the new study zoomed in on battery electrodes, which are made of nano-sized grains glommed together into particles. This constant back and forth makes particles swell, shrink and crack, gradually decreasing their ability to store charge, and fast charging. To look at this process in more detail, the team observed the behavior of cathode particles made of nickel, manganese and cobalt, a combination known as NMC that's one of the most widely used materials in electric vehicle batteries. Then they took particles to Lawrence Berkeley National Laboratory's Advanced Light Source to be examined with scanning X-ray transmission microscopy, which homes in on individual particles. The data from those experiments, along with information from mathematical models of fast charging and equations that describe the chemistry and physics of the process, were incorporated into scientific machine learning algorithms. Rather than having the computer directly figure out the model by simply feeding it data, as we did in the two previous studies, we taught the computer how to choose or learn the right equations, and thus the right physics, said Kong, who performed the modeling with MIT graduate student Hongbo Zh. The rich get richer effect. Until now, scientists had assumed that the differences between particles were insignificant and that their ability to store and release ions was limited by how fast lithium could move inside the particles, Kong said. In this way of seeing things, lithium ions flow in and out of all the particles at the same time and at roughly the but the new approach revealed that the particles themselves control how fast lithium ions move out of cathode particles when a battery charges, he said. Some particles immediately release a lot of their ions while others release very few or none at all. And the quick-to-release particles go on releasing ions at a faster rate than their neighbors, a positive feedback. Understanding this process on a fundamental level is an important step toward solving the fast-charging problem. The scientists say their new method has potential for improving the cost, storage. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.